And switch to board 3. Okay, bu gene donmuş tabii ki. All right, so here is the next lemma. W13 and W23. Remember, we have only 3 1 forms, right? 1 3, 1 2, and 2 3. The product of these two is nothing but the Gaussian curvature times theta 1, theta 2, and theta 1 3 wedge theta 1 plus theta 1 wedge 2 3 is 2 times the mean curvature times this gadget. Okay, this is the volume form on the two sphere, right? This computes the I shouldn't say maybe volume form, the area form. It computes the area, right, of a parallelogram spanned by two vectors in the tangent space. So actually this is, if you integrate this over the surface, you get the area of the surface, okay? Because at any point, it gives you the area of the two vectors of the parallelogram spanned by those two vectors. Okay. Yeah, probably you're right. In my notes, it is theta 1, but probably you're right. Okay, now by definition, the shape operator on E1 is just minus the covariant derivative of E3 by along E1. Remember that unit normal vector field is just E3, and shape operator is just the derivative minus the derivative of the normal vector along any vector you want. And we know that this is just minus 3 1 E1 sorry, plus or minus again 3 2 E2 no E1 E2 sorry E1 E2, and the shape operator on the second basis element is just minus the covariant derivative of E3 along E2. And what is this? This is minus, this time I have 3 2 E2 E1 minus no 3 3 1 pardon 3 1 aynı formül, sadece burada E2 var. And then 3 2 sorry E2 okay. Şu E1'ı taşıyoruz şurada. E2 koyduğumda da E2 var. All right. So the shape operator on these two basis elements are given like this. I don't have this parenthesis here. These are just some real numbers times basis operators, real numbers times basis vectors. Hence, the matrix representation of the shape operator at the point P in the orthonormal basis E1, E2 of the tangent space is what? What is the base? The matrix representation. Well, I compute S on the first basis element, and these are the coefficients. I write these coefficients as a column, right? So this is minus W31 E1 minus W32 E1. And then for the second basis element, its value is just this vector. So I write again this coefficients as the second column of my matrix representation. So minus 31 E2 minus 32 E1. No, E2, I'm sorry. So the same one forms computed for on E1 and E2. And what is the Gaussian curvature? Gaussian curvature is the determinant of this, right? Okay, so okay, now what was our lemma? Lemma was this. This two form compute is equal to this gadget, right? So, okay. All right, so hence K times theta 1 wedge theta 2 evaluated on the vectors E1, E2, E1, E2 is equal to what? This is just K, because, you know, this thing, okay, so this is just determinant of what? This element evaluated on this, which is 1. This element evaluated on this, 0. This element evaluated on this 1, and this element evaluated on this, which is this, and determinant is just 1. So this is just the Gaussian curvature, but Gaussian curvature is just determinant of S. So it is just this determinant, which is just W13, 31. Okay, yeah, I can do this. This is just W13 E1, right? This is just W13 E2. This is just W1, not 1. But 2, 3. No, yes, 2, 3. Sorry. And 2, 3 E2. Oh, this is 3, 1. Yeah. Sorry, I'm sorry. So, what is the determinant then? W13 E1, W23 E2 minus, this is again W23 E1. So W13 E2 and W23 E2. So what is this? This is nothing but W13 wedge W23 2, 3, this two form computed on E1 and E2, right? Why is that? Because this thing is just determinant of what? Determinant of this matrix. You compute this one on this one, so W1, 3, E1. I mean, it is just this one. Okay, yeah, right. This thing is just this gadget. So what we see is then this two form computed on these two vectors is the same as this two form computed on the same basis vectors. Hence, k times theta 1 wedge theta 2 is just W1 3 wedge W2 3. Okay. Yeah. It's a function, yes. K is a function. It's a real valued object. It's curvature. Yeah, K is a real valued function. K times this is two form. This is the area form. It gives us the area at any tangent space. So this is kind of weighted area. Okay, you have this area form, but you have a function on it. It tells us how you should modify your area form if your surface is banded. If it is flat, this will be just 0. So in that case, this gadget is just 0. So this is not good. This is not good to measure the area of a flat surface. Okay. For the cylinder also, this is 0. So it doesn't give you anything. But for the sphere, it will give you something. Okay. And there is a very good reason why this thing will be 0 for a flat surface. Okay. Sure. Gaussian curvature is negative for a saddle surface. Sometimes it is positive, sometimes it is negative. Actually, for centuries, maybe not for centuries, but for a long time, people thought there is no surface on which the curvature is negative. Okay. They thought Euclidean geometry explains everything. But then people came and said, well, that's not true. There are geometries where the curvature is negative. And later, many people did work on that. Started by, I guess, Lobachevsky, and then Gauss, and so on. Ama ilk önce inkar ettiler. First they denied that there is no such surface. Okay, so as far as I know, I am not 100% but sure, but Gauss was among those who didn't believe in those things first, but then he did tremendous work on those. Okay. I guess it's like Einstein. He didn't believe in quantum mechanics, right? Okay. The second statement, I'll leave it to you. So what's the second statement? It is about the scalar curvature. So you should get trace of this matrix. Okay. İsterseniz yapalım mı birazcık? Okay, now birazcık yapalım olmasa. So for the second statement, bu beni for the second statement, so theta 1 3 wedge theta 1 plus theta 1 wedge theta 2 3. No, we said theta 2, it should be right. Okay, now let's compute this on E1 E2 E1 E2. Well, by definition, so this wedge product is what? So this is just W1 3 E1 and then so okay, şöyle yazayım. This is just the determinant of W1 3 on E1 W1 3 on E2 and then theta 1 on E1 and theta 1 on E2 plus the determinant theta 2 on E1 theta 2 on E2 W23 on E1 W23 on E2. Well, these are dual forms, so this is just 0, this is 1, this is 0, and this is 1. So what we get is then şurası 0 verdi. Eksi W, so this is W13 E2 minus şurası 0 eksi W23 E1. Okay. Bunun neye eşit olması lazım? Trace is what? Trace is just so it is okay. Trace is W13 plus W13 E2 efendim? Evet. Onun trace'i ne olacak? Bir Şimdi ilk vektörü burada hesaplıyorum. Theta sonra evet. Tam da trace değil sanki. Değil mi? Trace 1, 3, E1 olması lazım. Eksi 2, 3, E2. E1 ile E2'nin yeri değişik. Onun bir anlamı yok ama. E1 ile E2'nin yeri değişik. Bir dakika. Burada bu ikisinin yerini değiştirirsek okay, so if I interchange E1 and E2, I will get here, these two will be interchanged. Changing the places of these two will reverse ya da yani şu ikisinin yerini değiştirmek, right? You may change this two, so it will pick up a minus sign. Şöyle diyeyim. Buraya E1, E2 koysaydık, sorry, E2, E1, I would have E1, E2. Yes. Peki, bir dakika. O zaman da eksi olacaktı. Yani şöyle aslında bu işaret tabii bu ikisinin yerini değiştirmek, bunun başına eksi koymak demek. O eksiyi buradan alırsam o şu demek yani so W1 3 wedge theta 1 theta 2 wedge W2 3 is equal to minus of this W1 3. Efendim? Yani şöyle mi diyorsun? I should make this 2, this one 1. Okay. Bu sefer burası 1 oldu. Burası 0. Burası 1. Burası 0. Okay. What is this then? W1 3 E1. W2 3 E2. Yeah, this is trace of S. Trace of S. Trace of S. So it is just 2H. 2H. What about, okay, 2H, and this is what we wanted to show. Yes. But here I have to make a correction. Then this should be 2 and this should be 1. Bunu bir kitaptan kontrol etsenize. Yani herhalde benim notlarımdaki yanlış. All right, so as a corollary of this, bu video beni as a corollary of these, so here let me just tell you that we changed these two indices, right? Okay, now by the second structural equation, dW12 was minus W13 wedge W23, which was Gauss's equation. And thus we have this corollary, d of W12, which is equal to minus 1 W13 wedge W23, but 13 wedge 23 is just the Gaussian curvature times d theta 1 d theta 2. Not d, I'm sorry, theta 1 theta 2. These are already one forms. Okay. A principal frame on a surface M is an adapted frame E1, E2, E3, so that E1 and E2 are principal vectors. So if you have an adapted frame, E1, E2, E3, so that E1 and E2 are principal directions. In other words, directions along which the Gaussian curvature, along which normal curvature are extreme, then this adapted frame is called a principal frame. Okay? Yani E1 ile 2 rastgele teğet vektörler değil ama principal vektörlerse o zaman ona principal frame diyoruz. So it's a special adapted frame, okay? Special adapted frame. Efendim? Doğrusu bu yani. Okay. So that's the correct one, okay? That's why we couldn't prove the wrong one, okay? The lemma is the following. It tells us when such a principal frame exists, if P is a non-umbilic point. So principal curvatures are not the same. If this is a point at which the principal curvatures are not the same, then point of a surface M in R3, then there exists a principal frame in a neighborhood of P in M. Yani eğer bir nokta non-umbilic ise, if the principal curvatures are not the same, then around that point one can find a principal frame. So suppose, you know, we have this surface, something like this. At any point here, principal curvatures are, so principal directions are like this, right? And this is like this. So K1 and K2, one of them is positive, the other one is negative. Therefore, it's non-umbilic. So E1 could be something like this. E2 could be something like this. Principal directions. They are the directions along which curvature changes the most, or I mean in the positive or negative sense, right? Extreme values of the curvature. Yes. Well, but I mean, you want to do this on a neighborhood. At any point, you can find a principal frame, of course. But the thing is that you want to do this in a continuous manner. And surfaces like sphere is not good. Why is that? Because any actually vector is principal. So you may choose some vectors at some point, but then at a nearby point, how you will choose those vectors so that they are continuous. Okay, so that's a problem. But if they are, if it is non-umbilic, then we know that at any point there are exactly two principal vectors. So each time I just choose those two principal vectors. I know that they are orthonormal. So I just choose those two vectors as my E1 and E2. But on a at the umbilic point, you don't know which ones to choose. Well, you can, but you know, so this doesn't tell you that you cannot choose such frame at a umbilic point. This tells us that if your point is non-umbilic, then certainly you can find a frame like this. Okay, this is an existence result. It doesn't tell us that you cannot do this for an umbilic surface. Proof by hypothesis, K1P and K12 are different, right? The principal curvatures are different, and thus since ki's are continuous functions, with k1 p different than k2 p, right? They are different on a neighborhood of the point P, right? These are continuous functions. If they disagree at a point, then they disagree on a neighborhood of that point, okay? So that's the statement, right? If they disagree at a point, then they disagree on a neighborhood of that point. Okay, let me choose the board, change the board. Okay. Principal directions are unit vectors along eigenvectors of the shape operator. Let S has matrix representation in some adapted frame. Let's say F1, F2, F3 as, so S is this, matrix entries, so S11, S12, S21, and S22. Well, S12 and 21 are the same because S is symmetric. Okay. Well, the characteristic equation of this S minus lambda I. What is this? This is just lambda squared minus trace of S times lambda plus determinant of S. So this is just lambda squared minus trace is just 2 times the mean curvature times lambda plus the Gaussian curvature. Okay. Now from this, what are the eigenvalues? Eigenvalues are the roots of this characteristic equation. So eigenvalues are just lambda 1 and lambda 2, right? The roots of this equation. And what are these? They are just, if you use, the expression for the roots of a quadratic equation, this is what you will get. And I know that, these are real numbers, and they are actually two distinct real numbers. So I have these two functions, and this also explains why K1 and K2 are actually continuous objects, because they are given, with such an expression where H and K are just some functions on the surface again. And what are the directions, principal directions? They are the eigenvectors. So principal directions are the eigenvectors associated to the eigenvalues. I will just build those, frames, principal frames. We just need to find the eigenvectors. Okay, now eigenvector means, so if I, so for the eigenvalue K1, the eigenvector, let's say, in this basis, F1, F2 has coordinates this. So what is this? Vector is actually A times F1 plus B times F2, okay, in this basis. Well, let's find A and B. What is this? This is S minus K1 times identity V1 is equal to 0. So what is this? This is just S times K1 identity. So this is S11 minus K1, S12, S12, S22 minus K1 times the vector AB is equal to 0, 0. I have two equations, but we know that actually the two equations are the same. So this is just A times S11 minus K1 plus B times S12 equals 0, right? The second equation is just the multiple of this. So this is the only equation actually. And from this, okay, so we may choose AB as what? I can choose my AB as follows: S12, yes, and then K1 minus S11. This is an eigenvector because if you plug it here, so S12 and here K1 minus S11. So the negative of this, you will get 0. So this is A times minus B plus B times A, which is 0. So eigenvector is just, this is my A times F1 plus B times F2, and I want a unit vector. That's therefore I just divide it by its length. So I can choose it this way. A is just S12 F1 plus K1 minus S11 F2 divided by the length of this vector. Similarly, we may choose, so this is just the first principal vector. So first element of my principal adapted frame, and E2 will be just V2, and let me tell you what the result is. K2 second eigenvector minus SS2 F1 plus S1 to F2 divided by length of this gadget. Now you see, I can find E1 and E2, this principal, vectors in a continuous manner, right? Here, Fi's are just my ordinary frame elements, right? It is an adapted frame, but not necessarily principal. Sij's are just entries of the shape operator. They are continuous functions. Therefore, E1 and E2 are continuous objects. Actually, they are differentiable objects on the surface. Okay. What about E3? Take E3 to be just E1 wedge E3, E2. Okay. So this is a principal adapted frame. Okay, now let me stop here. Next time I'll do just one more result on this, then we will finish this section, and then I'll pass to Gauss's work. All right, so let me stop.